Her calculations showed the sun was mostly hydrogen. But a famous astronomer told her finding was clearly not real. A vital photograph she took, unlocking the secret of life, was shown to competitors without her permission, and they got the Nobel. Another woman, after fleeing persecution, was the first to understand nuclear fission, yet her male colleague received the prize for their joint discovery. Imagine creating a life-saving treatment only for someone else to publish it as their own after your death. These aren't movie plots. They're real stories of incredible women scientists whose names you might not know, but whose work shapes our world every single day. Number 10. Lise Meitner. She explained nuclear fission, but her partner got the prize. Lise Meitner was born in Vienna in 1878, a time when higher education for women was extremely limited. Think about that. Wanting to understand the universe but being told the classroom door was mostly closed to you. Lise didn't let that stop her. She became one of the first women to study physics at the University of Vienna. After earning her doctorate, she moved to Berlin, hoping to study with Max Planck, a legend in physics. Planck, initially hesitant about women in science, eventually allowed her to attend his lectures. It was in Berlin that she began a 30-year collaboration with a chemist named Otto Hahn. For years they worked side by side, Lise focusing on the physics and Hahn on the chemistry of radioactive substances. Because she was a woman, Meitner initially had to work in a former carpenter's shop in the basement, and wasn't allowed in the main labs where male scientists worked. Their partnership was incredibly fruitful, leading to the discovery of the element protactinium in 1917. Then, history took a dark turn. In 1933, Adolf Hitler came to power in Germany. Meitner, who was of Jewish heritage, although she had converted to Protestantism, was initially protected by her Austrian citizenship. But when Germany annexed Austria in 1938, her situation became perilous. She had to flee Germany, leaving behind her life, her research, and her closest colleagues. She found refuge in Sweden, but it was a difficult transition. She had little equipment, faced prejudice against women in science, and was separated from her research partner, Hahn. Back in Berlin, Hahn, along with Fritz Strassmann, continued their experiments bombarding uranium with neutrons. They found some puzzling results. It seemed like barium, a much lighter element, was being produced. Hahn wrote to Meitner in Sweden, confused by these findings. It was Meitner, along with her nephew Otto Frisch, who was also a physicist, who pieced together the theoretical explanation while on a winter walk. They realized the uranium nucleus was splitting, a process Frisch coined nuclear fission. This was a monumental discovery. It released an enormous amount of energy and opened the door to the possibility of nuclear chain reactions. Imagine that moment of realization, understanding something that could change the world. Meitner and Frisch published their explanation in early 1939. Hahn and Strassmann had published their experimental results a bit earlier, but without the correct interpretation which Meitner provided. Yet, in 1944, the Nobel Prize in Chemistry for the discovery of nuclear fission was awarded to Otto Hahn alone. Meitner's crucial theoretical contribution, the actual understanding of what was happening, was overlooked by the Nobel Committee. Many scientists at the time, and historians since, have pointed to this as a significant omission. Lise Meitner never worked on the atomic bomb project. She was horrified by the destructive potential of her discovery. She famously said, "I will have nothing to do with a bomb." Element 109, Meitnerium, was named in her honor in 1997. A late but lasting recognition of her place in scientific history. Number 9. Rosalind Franklin, the chemist whose photo unlocked DNA's secrets. Rosalind Franklin was a brilliant chemist and X-ray crystallographer, born in London in 1920. From a young age, she showed a remarkable aptitude for science. She studied at Cambridge University at a time when women were awarded degrees titular, meaning they did the work but didn't get the same official degree as men until later. After Cambridge, she worked on the properties of coal research that was vital during World War II and earned her a PhD. Then she honed her skills in X-ray diffraction in Paris, becoming an expert in this technique which uses X-rays to determine the structure of molecules. In 1951, Franklin joined King's College London to work on the structure of DNA. Deoxyribonucleic acid, or DNA, was known to carry genetic information, but its three-dimensional structure was a mystery. At King's College, Franklin applied her X-ray diffraction expertise to DNA fibers. She and her HD student, Raymond Gosling, managed to obtain incredibly clear and detailed X-ray images of DNA. One image in particular, known as Photo 51, taken in 1952, was a breakthrough. It clearly showed an X shape, a pattern characteristic of a helical structure. Franklin's meticulous notebooks from this time reveal her careful analysis and her own deductions that DNA was likely a helix with phosphate groups on the outside. Meanwhile, at Cambridge University, two other scientists, James Watson and Francis Crick, were also trying to determine the structure of DNA, primarily by building physical models. They were in a race. The atmosphere at King's College was reportedly difficult for Franklin. Her relationship with her colleague, Maurice Wilkins, was strained. It was Wilkins who, without Franklin's knowledge or permission, showed Photo 51 to James Watson. For Watson, seeing that image was a revelation. He later wrote in his book, The Double Helix, that the instant I saw the picture, my mouth fell open and my pulse began to race. Photo 51, along with other data from a report Franklin had written that was also shared without her direct consent, provided crucial clues that helped Watson and Crick for their famous double helix model of DNA. In 1953, Watson and Crick published their model in the journal Nature. In the same issue, Franklin and Gosling and Wilkins and his colleagues published their own papers with their supporting data. Franklin's paper appeared last of the three, and some might say it read like an evidence piece for the Watson-Crick model rather than the foundational work it was. Franklin moved on from DNA research to do ground-ring work on the structure of viruses, including the tobacco mosaic virus and the polio virus. Tragically, Rosalind Franklin died of ovarian cancer in 1958 at the age of 37, possibly due to her work with X-rays. In 1962, James Watson, Francis Crick, and Maurice Wilkins were awarded the Nobel Prize in Physiology or Medicine for their discovery of the structure of DNA. Nobel Prizes are not awarded posthumously, so Franklin was not eligible. Many argue that her contribution was not fully acknowledged even during her lifetime or in the immediate aftermath of the Nobel Award. Number 8. Chien-Shiung Wu, the First Lady of Physics, who overturned a law of nature. Chien-Shiung Wu was born in a small town near Shanghai, China, in 1912. Her father, an advocate for girls' education, founded a school for girls which Chien-Shiung attended. She excelled academically and went on to study physics at National Central University in Nanjing. In 1936, she moved to the United States to pursue graduate studies, earning her AhD from the University of California, Berkeley, under Ernest Lawrence, a Nobel laureate. She was known for her incredible work ethic, meticulous experimental skills, and deep understanding of physics. During World War II, Wu joined the Manhattan Project, the top-secret American program to develop the atomic bomb. She worked at Columbia University, helping to develop a process for enriching uranium ore by separating uranium-235 from uranium-238. Her expertise in radiation detection and beta decay, a type of radioactivity, was already well established. After the war, she continued her research at Columbia, becoming a leading experimental physicist. Colleagues would call her when they needed an experiment done perfectly. Her most famous work came in the mid-1950s. Two theoretical physicists, Tsung-Dao Lee and Chien-Shiung Wu, questioned a widely accepted principle of physics called the conservation of parity. Parity, in simple terms, suggested that the laws of physics should be the same for an event and its mirror image, that nature shouldn't have a handedness at the subatomic level, particularly in weak nuclear force interactions like beta decay. Li and Yang theorized that parity might not be conserved in these weak interactions, but they needed experimental proof. They approached Chien-Shiung Wu, knowing her reputation as a brilliant and precise experimentalist. Wu designed a complex and elegant experiment. It involved cooling cobalt, 60 atoms to extremely low temperatures, close to absolute zero, to minimize thermal vibrations, and then aligning their nuclear spins in a strong magnetic field. She then observed the direction in which electrons were emitted during beta decay. If parity was conserved, the electrons should be emitted equally in all directions relative to the nuclear spin. That's not what she found. The experiment, conducted in late 1956 and early 1957 with collaborators from the National Bureau of Standards, showed definitively that more electrons were emitted in one direction than the other. Parity was not conserved in weak interactions. Nature, at this fundamental level, could tell left from right. This was a revolutionary discovery that shook the world of physics. In 1957, Tsung-Dao Lee and Chien-Shiung Wu received the Nobel Prize in Physics for their theoretical work, predicting parity violation. Chien-Shiung Wu, who designed and conducted the experiment that proved their theory, was not included in the prize. This omission was seen by many in the physics community as a significant oversight. Often called the First Lady of Physics, or the Chinese Marie Curie, continued her influential research, received many other prestigious awards, including the Wolf Prize in Physics and the National Medal of Science, and became the first woman president of the American Physical Society. Her experimental work was fundamental to our understanding of the weak nuclear force and the standard model of particle physics. Number 7. Emmy Noether, the mathematician who changed how we see physics. Amelie Emmy Noether, born in Erlangen, Germany in 1882, came from a mathematical family. Her father, Max Noether, was a mathematics professor. Despite this, her path to becoming one of the most influential mathematicians of the 20th century was filled with obstacles. At the time, women were not usually allowed to enroll officially in German universities. Emmy audited classes and finally, after rules changed, earned her PhD in mathematics from the University of Erlangen in 1907. Her dissertation was on algebraic invariant, a field she would later help revolutionize. For several years, Noether worked unpaid at the University of Erlangen, assisting her father. Her brilliance was recognized by leading mathematicians like David Hilbert and Felix Klein, who invited her to join the mathematics department at the University of Göttingen, then a world-leading center for mathematical research. However, the university's philosophical faculty resisted giving her an official teaching position because she was a woman. Hilbert famously defended her, reportedly exclaiming at a faculty meeting, "I do not see that the sex of the candidate is an argument against her admission as a privat docent lecturer. After all, we are a university, not a bathhouse." For several years, Noether lectured under Hilbert's name. Think about that. giving lectures filled with your own groundbreaking ideas, but someone else's name is on the course listing. It was during her time in Göttingen that Noether proved what is now known as Noether's theorem, published in 1918. This theorem is a cornerstone of modern theoretical physics. It establishes a profound connection between symmetries in nature and conservation laws. For example, it shows that if the laws of physics are the same, regardless of location, spatial symmetry, then momentum is conserved. If they are the same, regardless of time symmetry, then energy is conserved. This theorem provided a powerful new way to understand physical laws and is fundamental to fields like quantum mechanics and general relativity. Albert Einstein himself described her work as purely mathematical, but its implications for physics were immense. Beyond this famous theorem, Emmy Noether made monumental contributions to abstract algebra, particularly in the theory of rings, groups, and fields. She introduced concepts like Noetherian rings and Noetherian modules that are now fundamental. Her approach, focusing on abstract structures and general principles, reshaped mathematics. Einstein, in a letter to the New York Times after her death, called her the most significant creative mathematical genius thus far produced since the higher education of women began. In 1933, with the rise of the Nazi regime in Germany, Noether, who was Jewish, was dismissed from her position at Göttingen. She, like many other Jewish scholars, was forced to emigrate. She found a position at Bryn Mawr College in Pennsylvania, USA, and also lectured at the Institute for Advanced Study in Princeton. Tragically, her time in the United States was short. Emmy Noether died in 1935 at the age of 53 from complications after surgery. Her work continues to influence mathematics and physics profoundly. Number 6. Cecilia Payne-Gaposchkin. The astronomer who told us what stars are made of. Imagine looking up at the stars and wondering what they're made of. For centuries, people assumed stars were composed of the same elements as Earth, just much hotter. Cecilia Payne, born in England in 1900, was the one who first figured out they were wildly different. She developed an early interest in science, studying botany, physics, and chemistry at Cambridge University. However, Cambridge didn't grant degrees to women at that time, so despite completing her studies, she left without one. Seeking better opportunities for women in science, she moved to the United States in 1923. She received a fellowship to study at the Harvard College Observatory under its director Harlow Shapley. There she embarked on her doctoral research, focusing on stellar atmospheres. She meticulously analyzed the spectral lines from stars, the barcodes of light that reveal the chemical elements present. At the time, it was believed that the varying strengths of these lines in different stars indicated vastly different amounts of elements. Payne, however, applied new theories from quantum physics about atomic excitation and ionization to interpret the spectra. This was a groundbreaking approach. In her 1925 H80 dissertation, titled Stellar Atmospheres, Cecilia Payne concluded that hydrogen and helium were by far the most abundant elements in the stars, making up almost all of their mass. This was a radical idea. The prevailing scientific view, championed by prominent astronomers like Henry Norris Russell, was that the Sun and other stars had a chemical composition similar to Earth's. When Payne showed her dissertation to Russell, he advised her against her conclusion that hydrogen was the dominant element, writing that it was clearly impossible. Imagine the courage it took for a young PhD student to propose something so contrary to established belief. Because of this pressure, Payne added a sentence to her thesis, stating that her calculated high abundances of hydrogen and helium were almost certainly not real. However, Her work was otherwise so brilliant and comprehensive that her dissertation was later described by astronomer Otto Struve as undoubtedly the most brilliant PhD thesis ever written in astronomy. 4 years later, Henry Norris Russell, using different methods, arrived at the same conclusion about the sun's composition and published his findings. He did credit Payne's earlier work in his paper, but he is often widely credited with the discovery. Cecilia Payne, later Payne-Gaposchkin, after her marriage, continued her research at Harvard for her entire career, despite facing discrimination. For many years, she held low-paid, unofficial research positions. It wasn't until 1938 that she was given the formal title of astronomer, and it took until 1956 for her to become the first woman to be promoted to full professor from within Harvard's Faculty of Arts and Sciences, and also the first woman to chair a department there. Her pioneering work fundamentally changed our understanding of the universe. She showed us what the stars are truly made of. Number 5. Alice Ball, the chemist who found a leprosy treatment, only to have it stolen. Alice Augusta Ball was an African-American chemist born in Seattle, Washington in 1892. Her family moved to Hawaii in 1903, hoping the warmer climate would help her grandfather's arthritis. Though they returned to Seattle after a short time, Alice would later go back to Hawaii for her higher education. She earned undergraduate degrees in pharmaceutical chemistry and pharmacy from the University of Washington. Then, in 1914, she returned to Hawaii to pursue a master's degree in chemistry at the College of Hawaii, later the University of Hawaii. In 1915, she became the first woman and the first African-American to graduate with a master's degree from that institution. She was also offered a teaching and research position there, becoming its first female chemistry instructor. What an achievement for a young woman and a woman of color in the early 20th century. Her master's research focused on the chemical properties of the kava plant. But it was her subsequent work that would make a huge impact. Dr. Harry T. Hallman, an assistant surgeon at Kalihi Hospital in Hawaii, which treated patients with leprosy, now known as Hansen's disease, approached Alice. Time. Leprosy was a greatly feared disease, with no effective cure. Patients were often exiled to colonies like Kalaupapa on the island of Molokai. The existing treatment involved oil from the seeds of the Shalmugra tree. This oil had shown some promise, but it was difficult to administer. It was too thick to inject effectively, and when taken orally, it caused severe nausea. Patients hated it. Alice Ball, at just 23 years old, took on the challenge of making Shalmugra oil more effective. She developed a ground drain technique to create a water-soluble, injectable form of the oil. This involved isolating the ethyl esters of the fatty acids in the oil. Her method, which became known as the Ball method, allowed the oil to be absorbed by the body and begin working without the severe side effects of previous treatments. This was a major breakthrough. For the first time, people with Hansen's disease had a truly viable treatment that could alleviate their symptoms and in many cases allow them to return to their families and communities. Tragically, Alice Ball's life and promising career were cut short. She fell ill, possibly due to chlorine gas exposure in a lab accident, and returned to Seattle for treatment. She died there in December 1916 at the age of only 24. She never got to publish her revolutionary findings. After her death, Arthur L. Dean, who was the president of the College of Hawaii and also a chemist, continued her research. He managed to mass-produce the injectable Shalmugra extract. However, Dean published the findings as his own, calling the technique the Dean method, without giving any credit to Alice Ball for her crucial initial work. For decades, he received the accolades for the treatment. It wasn't until years later in the 1920s that Dr. Hahn, the surgeon who had originally approached Ball, spoke out. He wrote a paper giving Alice Ball the proper credit for her discovery, calling the technique the Ball method. Thanks to him, her story began to emerge. The Ball method remained the most effective treatment for Hansen's disease until the development of sulfone drugs in the 1940s. It helped thousands of people worldwide. In 2000, the University of Hawaii placed a bronze plaque on a shalmugra tree on campus in her honor, and February 29th is celebrated as Alice Ball Day in Hawaii. Number 4. Nettie Stevens, the biologist who discovered why you're a boy or a girl. Nettie Maria Stevens, born in Vermont in 1861, had an unconventional path to her scientific career. She worked as a teacher and librarian for many years to save money for further education. It wasn't until her 30s that she enrolled at Stanford University, completing her bachelor's and master's degrees there. She then went on to Bryn Mawr College for her PhD in biology, which she received in 1903 at the age of 41. Imagine the dedication to pursue your scientific passion later in life, at a time when opportunities for women in science were scarce. Stevens was a meticulous researcher, focused on cytology, the study of cells, and early genetics. Her most significant work centered on the question of sex determination. What makes an individual develop as male or female? At the time, many scientists believed environmental factors played a key role, or that it was a more complex, perhaps even random, process. Stevens decided to investigate chromosomes, the thread-like structures within cells that carry genetic information. She focused her research on insects, particularly the mealworm, Tenebrio molitor. She painstakingly prepared and examined slides of insect cells, carefully observing the chromosomes. In her studies of male mealworms, she noticed something consistent. Their reproductive cells contained chromosomes of different sizes. Specifically, she found that sperm cells either had a large chromosome or a small chromosome. Female mealworms, on the other hand, only had the large chromosome in their egg cells. When a sperm with the large chromosome fertilized an egg, which always had a large chromosome, the result was a female offspring, 2 large chromosomes. When a sperm with the small chromosome fertilized an egg, the result was a male offspring, 1 large, 1 small chromosome. Stevens concluded that chromosomes, not environmental factors, determined sex, and that the smaller chromosome, which she designated Y while the larger was %, was responsible for maleness. She published her findings in 1905 in a paper titled Studies in Spermatogenesis, with a special reference to the accessory chromosome. This was a landmark discovery. Around the same time, another prominent American biologist, Edmund Beecher Wilson, at Columbia University, was also studying sex determination and chromosomes. Wilson published similar findings slightly later or concurrently, and initially he was more cautious, suggesting environmental factors might still play a role alongside chromosomes. Stevens's conclusions were more direct and definitive about the chromosomal basis of sex. Over time, E.B. Wilson's work often received more prominence, and he is sometimes solely credited in textbooks with the discovery of XY sex determination. However, Nettie Stevens's independent research was crucial and clear. Thomas Hunt Morgan, a Nobel laureate and a leading geneticist of the era, and initially a skeptic of Stevens's chromosomal theory, later acknowledged her significant contribution. Unfortunately, Nettie Stevens's career was short. She died of breast cancer in 1912, only 9 years after receiving her Ph.D. and 7 years after her groundbreaking publication. Her work laid a fundamental piece of the groundwork for modern genetics. Number 3. Jocelyn Bell Burnell, the astrophysicist, who found pulsars in the stat. Dame Jocelyn Bell Burnell, born Susan Jocelyn Bell in Northern Ireland in 1943, developed an early interest in astronomy. She studied physics at the University of Glasgow, and then, in 1965, began her HD research in radio astronomy at Cambridge University. Her supervisor was Anthony Hewish. Together they were involved in constructing a massive new radio telescope, covering an area equivalent to about 57 tennis courts. Bell Burnell was hands-on in its construction, even helping to wield sledgehammers to install the posts. Her main task, once the telescope was operational, was to analyze the vast amounts of data it produced, literally miles of paper charts from a pen recorder. In 1967, while meticulously scanning these charts, Bell Burnell noticed something odd. It was a tiny, regular signal, a bit of scruff, as she called it, that didn't look like typical radio noise or known astronomical sources. It was a series of perfectly timed pulses, occurring every 1.33 seconds. Initially, she and Hewish considered earthly origins, then even the possibility of signals from an extraterrestrial civilization. They jokingly nicknamed the source LGM-1 for Little Green Men. Imagine the thrill and perhaps a bit of apprehension, thinking you might have found evidence of alien life. Bell Burnell continued her patient observations. Soon, she found another similar pulsing signal from a different part of the sky, then another and another. The discovery of multiple such sources made the Little Green Men hypothesis less likely. Pointed to a new type of natural astronomical object. The team realized these signals were coming from rapidly spinning, incredibly dense collapsed stars called neutron stars. These objects, only about 10 to 20 kilometers in diameter, but with more mass than our Sun, emit beams of radio waves from their magnetic poles. As they spin, these beams sweep across space, and if one happens to sweep past Earth, we detect it as a regular pulse, much like the beam from a lighthouse. These objects were named pulsars. The discovery of pulsars was a sensational astronomical finding. It provided the first observational evidence for the existence of neutron stars, which had been theorized decades earlier. A paper announcing the discovery was published in February 1968, with Hewish listed as the first author and Bell Burnell as the second, followed by 3 other contributors. In 1974, the Nobel Prize in Physics was awarded to Anthony Hewish and Martin Ryle, another radio astronomer at Cambridge who had developed pioneering telescope techniques. Jocelyn Bell Burnell, the PhD student who had first noticed the anomalous signals, spent months verifying them and correctly identified their celestial nature, was not included in the Nobel Prize. This omission sparked considerable debate at the time and continues to be discussed as an example of a significant contribution by a junior researcher, particularly a woman, being overlooked by the Nobel Committee. Bell Burnell herself has always spoken with grace and without bitterness about the Nobel decision, often noting that it was common at the time for senior scientists to receive awards for work done by their teams. She went on, to have a distinguished career in astrophysics, working in various fields of astronomy and holding professorships at several universities. In 2018, she was awarded the Special Breakthrough Prize in Fundamental Physics for her discovery of pulsars and her lifetime of scientific leadership. She chose to donate the entire £2.3 million prize money to fund PhD scholarships for women, underrepresented minorities, and refugee students in physics. Number 2. Maria Telx, the Sun Queen who wanted to power your house with sunshine. Maria Telx was born in Budapest, Hungary in 1900. From a young age, she was fascinated by the sun and its power. She studied physical chemistry at the University of Budapest, earning her BA in 1920 and her PhD in 1924. In 1925, she visited a relative in the United States and decided to stay, eventually becoming a U.S. citizen. She started her American career as a biophysicist at the Cleveland Clinic Foundation, investigating energy produced by living organisms. But her true passion, solar energy, soon took center stage. During the 1930s and 1940s, Telkes worked at various institutions, including Westinghouse Electric and then the Massachusetts Institute of Technology, MIT, focusing on thermoelectric devices, things that could convert heat into electricity. At MIT, she joined the Solar Energy Conversion Project. One of her key innovations was understanding how to store solar energy for use when the sun wasn't shining. This is a crucial problem for solar power. What do you do at night or on cloudy days? Telkes pioneered the use of salt hydrates like Glauber's salt, sodium sulfate decahydrate, for thermal storage. These materials absorb heat as they melt and release it as they solidify, maintaining a relatively constant temperature. Her most famous project was the Dover Sun House, built in Dover, Massachusetts in 1948. Working with architect Eleanor Raymond, Telkes designed and implemented the solar heating system for this experimental house. It was the first house to be heated entirely by the sun using her salt hydrate storage system. The system collected solar energy through large glass panels on the south-facing side, and the heat was stored in bins of Glauber's salt concealed within the walls. The Dover Sun House attracted considerable public attention and demonstrated the potential of solar energy for residential heating. Imagine living in a house powered by the sun back in the 1940s. While the system had some technical challenges over time, it was a pioneering effort. During World War II, Telkes developed a solar still for the U.S. Navy. This was a small inflatable device that could use solar energy to desalinate seawater, producing fresh drinking water for downed airmen or sailors on life rafts. This invention is credited with saving many lives. She also designed solar ovens, simple and effective devices that could cook food, using only sunlight. These were intended for use in developing countries or areas without reliable access to fuel. Maria Telkes was a true visionary, often called the Sun Queen for her relentless advocacy and practical development of solar technologies. She believed passionately in harnessing the sun's energy for everyday applications. Throughout her career, Telkes faced skepticism and sometimes resistance from colleagues in the male-dominated scientific and engineering fields. She left MIT in 1953 after disagreements over her solar energy research program. However, she continued her work at New York University, then at Curtiss-Wright Corporation, and later founded her own laboratory. She obtained over 20 patents during her lifetime, mostly related to solar energy devices and thermal storage. Maria Telkes worked tirelessly to make solar energy practical and accessible long before it became a mainstream concern. Her contributions laid much of the groundwork for the solar technologies we see today. Number 1. Katsuko Saruhashi, the geochemist who tracked nuclear fallout in the oceans. Katsuko Saruhashi was born in Tokyo, Japan, in 1920. As a young girl, watching raindrops slide down a window pane, she wondered what made it rain. This curiosity led her to pursue a career in science, a path not commonly taken by women in Japan at that time. She graduated from the Imperial Women's College of Science, now Toho University, in 1943 with a degree in chemistry. She then joined the Geochemical Laboratory of the Meteorological Research Institute. It was here that her groundbreaking work would take place. One of her first major achievements was in the field of oceanography. She became an expert in measuring the concentration of carbon dioxide, CO2, in seawater. This was a very complex task. In 1955, she developed a method to accurately determine the levels of carbonic acid, bicarbonate, and carbonate ions in seawater based on its temperature, Lise level, and chlorinity, a measure of salt content. This method, which produced a set of calculations known as Tsuruhashi's table, was adopted as a global standard and used by oceanographers worldwide for many years. It was a crucial tool for understanding the ocean's role in the carbon cycle, which is incredibly important for climate studies. In 1957, she became the first woman to earn a PhD in chemistry from the University of Tokyo for this work. The mid-20th century was the era of atmospheric nuclear weapons testing by various countries, including the United States and the Pacific Ocean. There were serious concerns about the spread of radioactive fallout. Tsuruhashi took on the challenge of measuring this contamination. She developed highly sensitive techniques to trace the movement of radioactive isotopes like strontium-90 and cesium-137 in seawater and in rainfall. Her research showed, for the first time, how this dangerous fallout was dispersing across the Pacific Ocean and even reaching Japan. She demonstrated that the radioactive materials did not mix evenly throughout the ocean waters as quickly as some had assumed, but instead traveled with ocean currents leading to areas of higher concentration. Her findings provided crucial evidence of the far-reaching dangers of nuclear testing. She showed that radioactive contamination from tests in the Marshall Islands could reach Japan within about 18 months. This research played a significant role in raising public awareness and putting pressure on governments, including the United States and the Soviet Union, to curb and eventually halt atmospheric nuclear testing. Her work highlighted the interconnectedness of global ecosystems and the long-range impact of human activities. Think about the courage it took to conduct and publish such politically sensitive research. Despite facing discrimination as a woman in a largely male scientific community in Japan, Katsuko Tsuruhashi persevered. She was a vocal advocate for women in science and for world peace. In 1980, she became the first woman elected to the Science Council of Japan. In 1981, she established the Tsuruhashi Prize, an annual award given to outstanding female Japanese scientists in the natural sciences to recognize their contributions and encourage others. She wanted to ensure that other women scientists received the recognition and support that had often been hard for her to find. Katsuko Tsuruhashi passed away in 2007, leaving a legacy of pioneering science and advocacy.